To calculate the ground impedance of a variable frequency drive, or VFD, cable that has 3 ground wires, several steps must be followed. These steps involve determining the resistance of a single ground wire, calculating the parallel equivalent resistance, and then finding the total ground impedance. The cable in question consists of 3 conductors and 3 bare grounds wrapped in a copper tape shield, with the grounds in continuous contact with the copper shield. Firstly, we need to determine the resistance of a single bare ground wire. This can be done using a multimeter or a loop resistance meter. Using one of these instruments, measure the resistance of one of the bare ground wires. Record this value, it will be used in subsequent calculations. Secondly, we determine the parallel equivalent resistance. If the copper tape shield effectively connects the bare grounds in parallel, the equivalent resistance will be 1/3 of the resistance of a single ground wire. This assumes that the copper tape shield provides a low resistance path connecting all 3 ground wires. Calculate this equivalent resistance by dividing the resistance of a single ground wire by 3. Thirdly, calculate the total ground impedance. The total ground impedance, denoted as Z, is the sum of the equivalent resistance, represented as R sub X, and the inductive reactance. The formula to calculate the total ground impedance is Z equals R sub X plus 2 times pi times F times L, where F is the operating frequency and L is the inductance of the cable. The inductance of the cable can be estimated using a rule of thumb. A common approximation is that L is approximately equal to 2 microhenries per foot. To find the total inductance, multiply 2 microhenries per foot by the length of the cable in feet. Now let's consider an example to illustrate this calculation. Suppose we have a VFD cable with the following parameters. The resistance of a single ground wire is 10 milliohms, and the length of the cable is 50 feet. First, we calculate the parallel equivalent resistance. Since there are 3 ground wires connected in parallel by the copper tape shield, the equivalent resistance, R sub X, is equal to 1/3 times 10 milliohms, which equals approximately 3.33 milliohms. Next, we calculate the inductance. Using the approximation of 2 microhenries per foot, the inductance L is equal to 2 microhenries per foot times 50 feet, which equals 100 microhenries. Then, we calculate the total ground impedance. Using the formula Z equals R sub X plus 2 times pi times F times L, where F is the operating frequency, let's assume a frequency of 60 Hz. The total ground impedance C is equal to 3.33 milliohms plus 2 times pi times 60 Hz times 100 microhenries, which is approximately equal to 12.5 milliohms. Therefore, based on these calculations, the ground impedance of the VFD cable with 3 ground wires is approximately 12.5 milliohms. It is important to note that this method assumes that the copper tape shield provides a low resistance connection between the bare grounds. The actual ground impedance may vary depending on the specific cable construction and environmental factors. Several factors can affect the ground impedance of VFD cables. One key factor is the quality and continuity of the connection between the ground wires and the copper tape shield. If the connection is poor, the equivalent resistance will be higher, leading to a higher overall ground impedance. Another factor is the operating frequency. As the frequency increases, the inductive reactance also increases, which in turn increases the ground impedance. The length of the cable also plays a role. Longer cables will have higher inductance, resulting in higher ground impedance. Additionally, the specific construction of the cable, including the type and thickness of the insulation and the arrangement of the conductors, can affect the inductance and therefore the ground impedance. Environmental factors such as temperature and humidity can also influence the ground impedance. Higher temperatures can increase the resistance of the conductors, while high humidity can affect the dielectric properties of the insulation. It's also essential to use appropriate measurement techniques and equipment to accurately determine the ground impedance. Using a multimeter or loop resistance meter for resistance measurements and understanding the principles of inductance measurement can help ensure the accuracy of the calculations. Remember that maintaining a low ground impedance is crucial for ensuring the proper functioning and safety of VFD systems. A low ground impedance helps to minimize the risk of electrical noise and interference, which can affect the performance of the VFD and connected equipment. It also provides a path for fault currents to flow back to the source, helping to trip circuit breakers or fuses in the event of a ground fault. In summary, calculating the ground impedance of VFD cable with multiple ground wires involves determining the resistance of individual ground wires, calculating the parallel equivalent resistance considering the copper tape shield, and using the formula Z equals R sub 8 plus 2 times pi times F times L to find the total ground impedance. Factors such as the quality of the shield connection, operating frequency, cable length, cable construction, and environmental conditions can all influence the ground impedance. By understanding these principles and performing accurate calculations, it is possible to ensure the proper grounding and safe operation of VFD systems. To delve deeper into this topic, consider exploring industry standards and guidelines related to VFD cable grounding and impedance. Resources from organizations like the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA, can provide additional insights and recommendations for best practices in VFD system design and installation. Additionally, consulting with experienced electrical engineers or VFD specialists can offer valuable guidance on specific applications and challenges related to ground impedance in VFD systems. Understanding and properly addressing ground impedance in VFD cables is essential for maintaining reliable and safe operation, reducing the risk of equipment damage, and ensuring compliance with relevant electrical codes and standards.